Is it? Oh, you can also check the audio with the headphones. Check if it's like. Can you hear me from here? Check. Hello. Hello. Check. Check.
Yeah, you can.
Yeah.
Yeah. It's a little faint though, so once you go over there, talk a little louder.
Okay. I can also turn it up a tad bit. Is it really loud here?
No.
No? Okay. Good. Okay. Good. Welcome, everyone. I'm going to be talking about Riemannian holonomy. A lot of the stuff I'll be talking about also just like works in general for general holonomy, but specific things like the Berger classification theorem will be specific for Riemannian holonomy, but I'll try to mention specific things when they apply in general, and then things that apply specifically to Riemannian holonomy. So holonomy is sort of the measure, it gives us like a group theoretic measure of how really curved a manifold is, a Riemannian manifold is. And that's sort of one of the things that we'll see is the sort of like relationship between parallel transport of things around Riemannian manifolds and how that relates to curvature, and why using Lie groups makes things a lot easier. So before getting into the meat of it, I'm just going to do some review of basic Riemannian geometry really quickly, try not to spend too much time on it. So we have a Riemannian manifold. It's just I'm going to assume everything's smooth today. So smooth Riemannian manifold, G, non-degenerate metric, Riemannian for now, although some things apply also for pseudo-Riemannian. Is a Riemannian manifold. We're also going to assume oriented most of the time, and I'll talk about the specific cases where we don't have orientation. We have a connection. In general, a connection is on a vector bundle, just some map that goes from smooth sections of your bundle into smooth sections of your bundle tensored with the cotangent bundle of the underlying manifold, where E.
Sorry, sections or C infinity?
Yeah, smooth sections, yeah.
Oh, sorry, you just said into sections of E.
Yeah, sections of like this bundle, I guess, or like, yeah, C infinity. I guess you can write gamma here, right?
Yeah.
Yeah, if you think of this thing as a bundle, yeah.
Yep. It just has to be like C infinity linear.
Yeah, smooth section, everything is smooth, yeah. Yeah, where this is here is a smooth vector bundle. Smooth vector bundle. So connection is just a map like this, such that whenever I have a function times some section V, I have that this will be f nano V plus V tensored with df. Okay. So that's a connection, and a curvature. Where my computer is? Oh, there it is. I'm sort of like moving through this stuff, assuming that you guys know some of the connection and like Riemannian stuff. But if you have any questions about this, let me know. Okay, so that's a connection on a general vector bundle. For us, for this talk, we'll generally be interested in the tangent bundle. But we also have what's called the curvature tensor, okay, R, which takes two sections it takes two sections of your E. How do you do this? It takes two sections of E into a endomorphism of E. Okay, and how does it do that? Can you guys see down here? Or should I? Yeah. It essentially will take V and W, or sorry, it takes two vector fields. It takes two vector fields, sections of the tangent bundle. And returns an endomorphism of E. And it does that in the following way. If sigma is a section, then R of VW is nabla V, nabla W, sigma minus nabla W nabla V, sigma minus nabla VW sigma.
Sorry, what does nabla sub V mean? What is that notation?
Yes, okay, yeah, good question. So nabla sub V means do nabla sigma, and now this thing has one form in it, and feed it a vector V from the tangent bundle. And so that's what we call nabla V. So you're just contracting with a vector. And so yeah, that's good. That gives us an operation nabla W, and it satisfies all these like nice relations. That is like it's C infinity linear in this object here. Okay, yeah.
What is the notation for the curvature tensor maps from what to?
Vector field.
Oh yeah, chi. Yeah, this X thing. Matfrac. Yeah, thanks. Is smooth sections of TM.
I don't think it is math frac, but it's kind of.
I think it was math cal.
Math cal X.
Some symbol X.
No, I don't think so.
Either, no.
I would. No, but math frac?
Math frac is goofy. It would be like way more.
Yeah, I don't think it's math frac.
It's like
No.
math script maybe, something like that. Math script.
Var X.
Okay, good. Okay, any other questions? Yeah, good. Okay, good. So that's the curvature tensor in general. Again, today mostly we're going to be looking at the tangent bundle. So let's look at specifically like things that happen for the tangent bundle of some manifold. So if our bundle is just like Tm for some smooth manifold M, then we'll notice that here in general, so like we said here, we could only take these things to be in Tm, but this thing had to be a section of E. But the nice thing about the tangent bundle is that all of these objects live in the same sort of space. So we actually get an additional tensor called the torsion T, which also takes two vector fields. In this case, it's the vector fields because they're sections of the tangent bundle, and it's going to be an endomorphism also, or is it right? No, it takes TVW. It's like nabla V W minus nabla WV minus VW. Okay, so it takes two vector fields and returns a vector field.
Can you write this notation in terms of the commutator bracket? Can you write like bracket nabla b, nabla I guess it would be more for that one down there.
Yeah.
Could you write that as like bracket nabla b, nabla w applied to sigma? Or,
Like this?
yeah, like, is that something people write or no?
Sure, yeah, that's okay.
Oh, okay.
Yeah. Minus,
Minus, yeah,
nabla like this, BW.
Yeah.
Yep. Yeah, it's, yeah, you can write it like that. It's also like an interpretation of curvature. Curvature is sort of like how much these fail to commute basically with each other.
Okay.
How much the
Yeah.
covariant derivatives fail to commute. Yep.
Another like side question, sorry. When people say torsion free, is
Yeah.
this the torsion they're talking about?
This is the torsion.
Okay.
Yeah, exactly. Yeah, and this thing also basically tells you, like when it vanishes, you're basically saying that doing this sort of thing, like doing the commutator or like sort of like differentiation of like W by V and V by W is the same thing as doing the Lie bracket. So just that those two things will coincide. Okay, good. So that's a torsion tensor. And question?
Yeah.
Yeah.
So, if we were to write out the V bracket of VW,
Yeah.
that would be VW plus WV, right?
Yeah.
In what is that? What object is that?
It's a vector.
It's a vector.
Mm-hmm.
I see.
Yeah, because this is again vector field cross vector field into the sections, right?
Sorry?
It's vector field cross vector field into the sections, right?
Yes.
Yeah.
It's it takes two vector fields and returns a vector field. So it's like a 2-1 tensor. 2-1. And this is a, well, this is not a, like, this is like, yeah, two endomorphism value, yeah, whatever. Yeah, this is a 2-1 tensor. Okay. Good. Okay. Good. So for the case of Riemannian geometry, we're interested in torsion-free connections, torsion-free and metric connections. So-called Levi-Civita connection. Okay. What does this mean? Torsion-free just means that this torsion tensor vanishes on your manifold, and metric connection means nabla G equals 0. And now you might ask the question, what does nabla G mean? We've defined nabla for like sections of like E or something, or like here we define it for Tm. You can extend the definition of nabla to tensors in general by first like having this sort of rule where you have like a Leibniz rule on tensor products, and this sort of like rule on forms. I'll just write one for the one forms, which is that for a one form, this thing, if it eats an x, will be, it'll be, let's see, x, hold on, yeah, alpha of nabla x minus alpha nabla x, yeah, plus, oh, I think I have to feed it one more thing.
And that minus sign is like normally like -1 to the power of k times something, where k is the form.
No, actually. The idea being here that, like, okay, so if I have an alpha form, I can always feed that a vector. And the idea is that, like, if I act y on this, I would want this to be the covariant derivative of alpha. So first differentiate alpha, and then feed it x. Plus, so we differentiated alpha, but then now you also want to differentiate x. So do alpha of nabla yx. Okay, and then from this you can solve for this guy.
Oh, I see.
Like,
Yeah.
So in general, it'll just be like if you had more x, y, z, like for a general form, you just like keep adding plus, 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 and then here it'll all be minuses when you move them all over. Okay. So yeah, with these two rules, you can essentially have induced connections on all tensor bundles on your manifold. And so specifically, we can talk about what it means to take the covariant derivative of G and say that it's equal to 0. Okay? So these two conditions give us what's called the Levi-Civita connection. And theorem is that, I guess we kind of talked about this last time, but I wanted to do a little more of the bundles just so that we're making, is Levi-Civita connection is unique. Well, it exists, of course, and is unique for any Riemannian manifold H. Okay. And the proof sketch behind this, I'll leave a proof sketch because we can get to the actual topics, is that you can actually write down, so basically the torsion vanishing condition just tells me that nabla xy minus nabla yx is the same thing as the brackets. So this will be a condition that's like nice when you rearrange for stuff in order to like get rid of first order covariant derivative and write things in terms of the brackets. The more important condition is the metric condition, and essentially you can write down this expression nabla x of g of yz, and write down cyclic permutations of this expression, so nabla z gxy and the third one, and then you add them up, and essentially you end up getting a this expression. So yeah, plus cyclic permutations. I think the last one might have a minus sign, but regardless, you get a expression for this guy, and it's I'll write it out. It's kind of a long expression, but this y and this g. C minus g x C y. Okay. How did we obtain this expression? We wrote down this thing. I used this sort of like this sort of relation that I wrote down here with how to take the covariant derivative of a 2 form and take the cyclic permutations, add them up. And I also reduce all first order relations that look like this in order to obtain these Lie brackets that you see in the left lines. And so with this, yeah.
A bunch of parentheses. I think you're missing a lot of close.
Wait, yeah.
Oh, yeah.
Yeah, okay. Yeah.
On the first one. line maybe as well, like x of g is
Very
y.
likely.
Is that
There.
Yeah.
Is that right?
Yeah, it should be all.
Yeah. Okay. Yeah. Thanks.
The last term as well.
This one.
Oh, no,
No, that's fine.
Yeah,
It's x comma and then the bracket.
True, true.
Mm.
all of that is being halved? So like,
All of that is being halved. Yeah. So it's like 2 times that side equals this. Yeah. Yeah. Essentially, like when you add add these 2 and then subtract the next one, there's only like there ends up just being this 2 of these terms and everything else cancels. And yeah, this is what you get. And why is this useful? It's because essentially computation, just like pure computation, shows that if I call this thing omega xy of z, okay, omega xy is c infinity linear. Okay, that's just the computation that one can check. And since omega xy is c infinity linear, we have this sort of like Riesz representation like theorem that this thing on z, there exists a unique vector field v such that this thing is equal to g of vz. Or in other words, omega xy is equal to v sharp or flat or something. One of the 2. Musical isomorphism. And this is because if you remember last time when I was speaking about the Hodge stuff, these musical isomorphisms are isomorphisms, and so therefore there's like a 1-to-1 correspondence between forms and thing, and this is the explicit correspondence. But since omega xy is already like g of nabla xy with z, that means that there exists a unique v, which is like nabla x of y. So there's only like one way to define nabla x of y for every x and y. So that's the proof sketch of the existence and uniqueness of the Lagrange-Theta connection. Okay. Okay, so now that our sort of like review of Riemannian geometry is done, we're going to do more Riemannian geometry, but it's not going to be review. We're going to define what parallel transport is. So, parallel transport. So again, parallel transport is also defined on a general bundle with a general sort of connection. But for now, I'll do it for a vector bundle, and later we'll even be more specific on a tangent bundle. But essentially, given a S0 in EP, let's say we have this vector bundle EIM, and we have a connection nabla on E. We can ask the question basically, can we find a section given a curve, I should say. Yeah. Given a curve gamma.
Sorry, so what was this not again?
Sorry?
What was S not again?
This is just some point in one of the fibers of your bundle.
Oh, sure, okay.
Yeah.
EP just means it's the fiber above the point P. Or...
At the point P and M. Yeah.
Oh, yeah. We use that notation too, sorry.
Yeah. So given some kind of curve, gamma, so here's M, I have this point P, and I have this fiber EP that sits above P, and I have this point S0 that lives in the fiber, and I have a curve, gamma, that begins at P and ends somewhere, let's say it ends at Q. The idea of parallel transport is we want to sort of get a lift for this curve. We want to lift this curve up to the bundle E. So the question is, given this sort of curve gamma from 0, 1 to n, can we obtain kind of like lift? Can we lift? Can we lift gamma in a very special way, in the sense that it's going to be what we call horizontal, which means that basically we end up getting a section, once we lift gamma, we get a section of this bundle, and we know now that we can actually apply this nabla thing to these sections, and we will require that nabla of this section that we want to get to be 0. Okay. So yeah, parallel transport is asking for a section.
S naught or S?
S will be this section that we're going to obtain, which is here. S naught is just a point in.
Oh, you apply the connection onto the whole.
Yeah, onto the whole.
Onto the
like,
lifted sort of curve. Oh, okay.
Yeah, because this like lifted curve is just going to be a section of. It's going to be a section rather of like just the bundle restricted to the curve, or like the pullback bundle to the curve, technically speaking. And yeah, we're asking if we can find a section of that such that nabla is 0, or it's also called we call it parallel, the parallel condition.
I
Okay.
don't really see why we want that though.
Why we would want that?
Yeah.
I mean, so you generally
Or what is that telling us, rather? I guess instead of why we want it. What is nabla S actually telling us?
Well, it's a way to differentiate sections nablas, right? So this is just telling you that, now that you have a way to differentiate something, this is telling you that this thing is actually like constant along.
Oh, along that curve.
Yeah. Yeah.
So the nabla S, it's really, like you said, it's really a section that's just over the curve, like everything's actually pulled back to 0, 1.
Yes. Yes.
So is your nabla, is there only like a one-dimensional space of vector fields that you can plug in?
That's right.
Okay.
Yeah. That's right. Yeah. So like when you, it's actually just to the pullback of E. This is the bundle in which you're a section of, and yeah, like technically, like this thing, there's only like one parameter. It's like ddt that you can. Some people will call it d by dt, I think. But yeah, there's only like one vector field for which you can differentiate. It's basically like the derivative along the curve itself, basically. Yeah.
If you want to repeat the answer, usually like all these things are going to be pulled back. So this nabla is not really the nabla on the E,
Yeah.
it's the nabla.
It's not.
Everything.
It's like gamma star nabla,
Yeah.
like a pullback.
Great.
Yeah. Good. Yeah, sorry, there technically should be like, you could write like E and like E star and blah, blah, like all the nabla decorations, but it's always omitted. So. Okay. So the question is like, we can actually like do this. We can actually find there exists a unique section. There exists a unique section S with this condition that if I started as 0, there's a unique section such that the section at that point P is as 0, and it's parallel along the curve gamma. And why is that true? Well, that's just because this equation here, along with the condition that S at the point P is equal to S0, just gives you a system of differential equations, and you can use like just like the uniqueness in existence theorems of ODEs to show that you'll have a unique section. Okay. So what's this good for? This actually ends up giving us a map that goes from the fiber at P to the fiber at Q. Here we'll basically like have, I'll call it S1, which is just a section at the end, and this will be sitting at EQ. And so actually, given any sort of like point, given any sort of curve that connects the points P and Q, we have a map that takes you from EP to EQ. So we have this map P gamma that goes from EP to EQ whenever basically gamma of 0 equals P and gamma of 1 equals Q. And what is this map? How do you apply this map? The map is just you find the section and then you take S0 and then map it to whatever S1 is. And this is what we would call a parallel transport map.
You could still do it, like you would just get a non-homogeneous system of equations if you didn't have
I'm sorry?
a parallel condition, right? It
Or
would
like
just
if
be a
you,
system of non-homogeneous DEs.
what if you,
For delta S not equal to 0, you can still do that, no? Or what happens if it's not 0? What happens?
well, you need to specify some kind of condition on the section to get a unique transport, right?
Oh, sure. Okay. So like the initial conditions, basically.
Well, not just the condition, but you also have to give an equation to be able to like get a unique transport, right? So that's why like you can require like nabla s equals 0. Okay. Good. Any questions about this? Yeah.
Like you have a path from P to Q, and then you have like a smooth homotopy of that path.
Mhm.
Like how much does this thing change?
Yeah, good. So there is a sort of connection with the fundamental group, which is that essentially when sorry, so your question was if you have a curve that's homotopic to this, how much does this map change?
Yeah, like even like if it makes it simpler, assume that P equals Q. So you have
Yeah.
two loops that are homotopic.
Yes.
The induced map, like, does that have to live in a special group, or is this?
Yeah, great. That's exactly what I'm gonna do next. That's the holonomy group, actually. So, yeah, I'll talk about that in a second if that's okay.
Okay.
Yeah,
Yes.
yeah. And remind me if I forget about that, please. Okay. Any other questions? Okay. Good. So yeah, we'll talk specifically now about the case where P is equal to Q. So specifically, when you have P is equal to Q, we actually obtain an endomorphism. It's actually an automorphism from EP to itself. Okay, so this is when we have gamma 0 equals gamma 1 equals P. Okay, so this sort of gives a map from EP to itself. So these ones here, these do form a group which we'll call whole P. So these are all these P gammas for curves gamma that have gamma of 0 equals gamma of 1 equals P. Okay. So these are these parallel transports that all start and end at P. They form a group called whole P. And the composition is when you multiply P gamma times P delta, it's P gamma star delta, where this is like the usual one from like topology by like composing the two paths. Why is it a group? Well, because if I do the inverse of gamma, which is just going backwards, just by looking at the properties of the dE that you have, it's a first order dE, it actually ends up giving you the inverse map of gamma. And and then this ends up just giving you a sort of group because they're all just like automorphisms of it. Okay, so this is actually a subgroup of automorphisms. Yeah.
Is there any worry about because at the point that these two meet, my curve might not be smooth?
Yeah.
Or is there something to worry about that? Or?
No, that's okay. This is all for like piecewise smooth curves. So as long as it's piecewise smooth, everything is okay. Yeah.
Have people investigated when it wasn't exactly smooth? Like, what happens if not?
If what?
If they're not smooth?
If they're not smooth, well, they can't not be smooth because you need the smoothness to well, you need at least piecewise smoothness to find the like solutions to the dE, right?
It's just your solution is just going to be a piece of gamma.
Yeah.
Oh, okay.
By sort of like.
Consistent boundary conditions.
Okay.
Exactly. Yeah. Good questions, though. Okay. Good. Yeah. So now we have one of these groups for each point in the manifold M, and so the question is like, we want to like relate them. Like, we don't want to be working with like a million of these. The idea is that like if I have 2 points P and Q, and I have some sort of gamma that connects them, I'll just write it like this. Then we can actually, this gives us like this map P gamma, like we said. And one can show that Hall Q is actually just equal to P gamma. Let's see how this, I don't want to mess this up. I think it's like P gamma, and then Hall P, and then P gamma inverse. So you're based at Q, no, yeah, I did it wrong. Yeah, you're based at Q. So you first go back to P. So I'll draw the picture here. You're based at Q. You first go to P. You do your loop around P, and then you go back. So this shows that basically any loop or any holonomy at Q is going to be living inside this group here, holonomy at P, and of course the other way around is the same thing. You have the other inclusion, and so they're actually the same. They're the same groups. So whenever you have 2 points that can be connected by a curve, the holonomy groups are actually the same. Good. So basically, we have one holonomy group per path component of our manifold. Yeah.
Why don't you just have like the holonomy category?
Holonomy category. Or like what?
So like instead of focusing on each point, it's like the fundamental group point. You just consider
Yeah.
all points at once.
Yeah, there is such things. I haven't.
Partial composition.
Yeah, like a groupoid, right?
Yeah.
Yeah.
Except like, yeah, I guess in this case, yeah, if the HOMs are just all possible P gamma for some path,
Yeah.
then it actually would be a groupoid and you don't have to worry about homotopic classes.
Yeah. There's work been done on this, yeah, for sure. I know there's work been done. I think they call it two-holonomy or something.
Two-holonomy?
Yeah. I don't know much about it, but I know there's been some interesting work on that, yeah, for sure.
think that also falls in. There's this other thing called holonomy groupoid. I'm sure that's how it's
Holonomy
called.
groupoid, yeah.
But it regards more. I think it's a bit more general, but I think your case lies down in this one as well.
Okay. I mean, it seems like a natural thing to do. So you don't, this like specifically, you don't have to mess around with like, identifying groups at different points.
Yeah.
What is the next one?
To like go to like the groupoid version instead of like fixing the point and considering everything at that point, like going to like the groupoid where your category, the objects are points, and your homomorphisms are like
Possible
these
deviations.
things induced by paths between the points. So it's like the fundamental groupoid of a topological space.
But these things you can get from those?
I mean, like the operators, the p gammas. So like your hom is a p gamma for some gamma from the first base point to the other.
I wonder what that would lead to, like other than just making it easier to work with.
Yeah, like convenience and
Convenience, yeah. But
Yeah.
I wonder what you could do with that. If there's any interesting groupoid stuff you can do.
Yeah, I mean, there's been a general like push in this stuff, like in physics, where like you do things with groupoids, like especially because like there's a lot of things in physics that are like path dependent kind of thing,
Mhm.
and then we always end up having to do loops rather than paths because paths are difficult. So yeah, but yeah, you have to do a lot of category theory for that stuff. I guess it's just been done like very recently. So good. Okay. So generally we'll have this thing called Hall 0, which is just going to be the the identity connected component of Hall P. Okay, so Hall P in general is not connected. Okay, and but it's going to be I didn't mention this. It's going to be a Lie group. I should have said this here. Where did I write it? Here, yes. So this is Hall P is a Lie group. It's clear that it's a subgroup of the automorphisms of EP. There's a bit more work to be done to say that it's a Lie subgroup, but one can show just from like the sort of theorems that it's like closed and stuff, that it's actually like a proper like Lie subgroup. So it has a Lie algebra and it's all like the usual. It has all the good properties that Lie groups have.
So it's like a finite dimensional Lie group because it's in this automorphism of this finite dimensional vector space.
Wait, why is it finite dimensional?
Well, if each of them, like,
Oh, it is finite dimensional, yeah.
yeah, because it's a subgroup of like odd EP, and that's a finite dimensional space. Even though it seems like if you have an arbitrary curve, there's like uncountably many different types of perturbations you can wiggle this curve by.
Yes.
But there's still only like a finite range of freedom on your operator.
That's right. That's right.
Wild.
And that sort of comes to the fact that basically, if you take Hall P and mod out by Hall P0, this is just the fundamental group. This is pi 1 m at P. Or no, sorry, it's not equal to. There's a surjective mapping into here. Is that right? That's right. I think that's it.
As if like two paths are homotopic, and the induced operators are going to be in the same path component.
Yes, exactly. Exactly. And so essentially when M is simply connected, this will be the whole thing. All B will be the entire thing, and it will be connected. Otherwise, basically like Hall P is an extension of this identity connected component by some discrete group. Yeah.
What is the identity connected component?
The identity connected component is the connected component that contains the identity element. So this is a Lie group, so it contains an identity, this is a Lie group, and so it contains an identity element. But in general, it's not connected. Let's say it has multiple components, like the identity is here. This will be the identity connected component.
Okay, this would probably be a really stupid question, but why is it not generally not connected? Because like I can't imagine, like if Hall P is just all the maps P gamma, so how would we ever like disconnect? How are we not connected?
So, I mean, one very easy case is like if the manifold itself is disconnected,
Oh,
right?
yeah, you're right. You're right.
Yeah, then
I didn't
like,
think about that.
yeah. But then even if it's connected, there are paths that can't be shrunk into each other because of this
Oh, because of the holes. Yeah.
fundamental
Okay.
group. And that actually leads to just like different components of Hall P, because those paths can't be like, there's no paths between those paths, basically. There's no smooth paths between those paths. Yeah. So yeah, that's another reason why you get like disconnected components. But if your manifold is simply connected, so if this thing is trivial, if pi1 trivial, then basically Hall P is connected. Connected. Okay. And
And hence, whole P0 is whole P.
correct. Hall P0 is the same as Hall P. Exactly.
So, for a whole P0, like you take the identity in like one of those things, and is it like direct summed with the identity of the other ones, or is it just one because the identity is unique?
Is it, sorry?
So like you marked a point on that.
Like the identity.
Yeah, the identity has to be in one of the connected components of Hall P, right?
Okay, and because the identity is unique, there's only one.
There's only one, yeah, because the identity is unique, yeah.
Okay.
Good. Yeah. Any other questions?
I mean, it still doesn't see why it's finite dimensional as a
Why it's finite dimensional?
yeah.
I mean, it has to be because, well, it's a subgroup of RTP, right?
So, yeah.
And RTP is finite dimensional, so yeah.
It's a very.
It's like
cop-out.
the yeah. I mean, like yeah. I guess the reason that it's a Lie subgroup, I didn't really put that in, but that's yeah. But the finite dimensional, I guess, is just because RTP is itself finite dimensional.
They all have like linear transformations, and there's only so many of those, I guess.
Yeah. Yeah.
Okay.
Good. Okay. Very good. All right. So this is all again like a lot of this holonomy stuff is very general to any bundle. I think so far I haven't assumed for the holonomy stuff Riemannian. But we can specify that basically like we want to do Riemannian holonomy by saying we're looking specifically at the Levi-Civita connection, and we're looking at the holonomy group of that Levi-Civita connection. But I also have this theorem which is general to all of these things, but I only stated it in terms of, because I only knew how to state it in terms of the Riemannian one. But I'll write it down here. This is the Ambrose-Singer theorem. So yeah, like I said, it generalizes for non-Riemannian as well, but the one I wrote down here is specifically for the Riemannian case. Okay, so this is a Lie group, like we said. So it has a Lie algebra called little Hall B. This is the Lie algebra of Hall P. Okay. And this Lie algebra is actually just spanned by P gamma inverse R Q Z P gamma such that Q is just some point in the manifold and UV are vectors in TQN. And gamma is some curve from P to Q. Okay.
And R was that metric?
R is the curvature tensor.
Curvature, sorry.
Yeah, the curvature tensor. Okay. So yeah.
Just to clarify, just to make sure I know what you mean by like the Riemannian holonomy, does that just
Yeah.
mean that the connection we're using is the Libby-Civita?
The Libby-Civita connection. Yeah. So for
there's some connection on some level.
yeah. So for Riemannian holonomy, basically we have a nebula LC. We call it Libby-Civita connection, and yeah, we use that on some Riemannian manifolds, and then all the parallel transports and holonomy groups are the ones of the Libby-Civita connection. Okay. So yeah, we said that Hall P is a Lie group, and so therefore it has a Lie algebra. We're going to call that little Hall P, and the theorem by Ambrose and Singer is that essentially that Lie algebra is generated by the curvature tensor being transported around by any curve that transports some points around the manifold. Okay. And again, this is like specifically like because we're doing UV and TQM and stuff. This is like for Riemannian, but you can see how this can easily like generalize to more general connections, more general bundles. So I have a proof sketch as well. These proofs are like usually quite long, so I can only do proof sketches in the time constraints. So a proof sketch, I guess. Essentially, we have that, we call that whole B is a subgroup of automorphisms of BP. And so therefore, whatever this Lie algebra is, and we said that this is a Lie subgroup, so this Lie algebra will actually be a Lie algebra of whatever the Lie algebra of automorphisms is, which is just n of EP. Okay. And recall that basically this guy, the curvature tensor, eats two vectors and gives us an endomorphism of EP. And so this actually makes sense to talk about this thing. And the theorem goes by picking two vectors v and w in just vector fields, but we pick them for simplicity to commute. Okay, so pick two vector fields that commute. So since these two vector fields commute, if I'm here at P, I follow V first, and then I follow W by flow, like all of these are flows. And then I do the same thing backwards. I follow V, and I follow W by flow. Excuse me, because these commute, I end up closing the curve. So, so this is V, W, the flows of these two vector fields. So I actually get a closed loop, and I can compute this P gamma as long as I sort of flow by a very small amount. So we flow by just an epsilon. and you flow by just an epsilon so that you can actually have all of this sitting inside of a coordinate patch, and that you can compute everything with coordinates. And once you do that, you find that these holonomies that sit in here look like they have to be like the identity to first degree in epsilon, and then you get epsilon squared RVW, and then higher order terms in epsilon. Okay. So from here, basically, we see that if you subtract the identity and divide by epsilon squared, take the limit as epsilon goes to 0, we get RVW. Okay. And so what this shows basically is that, so this is not obviously not an arbitrary curve, but if we wanted an arbitrary curve, we can always decompose into vector fields that commute, and then is that how it works? Hold on. Let me check what this thing said. Let's check here. Yeah, no, it's not here. Yeah, there was something about like, yeah, you work it out for vector, and now I'm like looking at it, it doesn't make sense actually.
I also don't know like where you get, how do you know you can just find two commuting vector fields that aren't 0 or whatever?
Yeah, so the idea is that the idea is that like you first will do it for something like this, for two vector fields that do commute, and then you do it for two vector fields that do commute, and then in general, like you'll there's some generalization that I'm forgetting how it exactly works right now, but yeah, I don't remember exactly how it generalizes for non-commuting stuff. Yeah, sorry, I forgot about that. Proof sketch, I guess. Okay, but okay, ignoring that bit, the idea is that here we're taking a sort of like up to reparameterization by epsilons to like root epsilon stuff, because you can just like flow by root epsilon instead, and then this will be an epsilon, and then this shows you that basically like these p gammas are generated by this curvature tensor, and that's why we end up getting this sort of relation here. Yeah, maybe I'll write up a note on the proof of this, or like give a source on this later, because I'm just like blanking on how it generalizes, but yeah. Okay, good. Good. Any questions about that one? I'm sure there's a lot of questions about that actually, but. Do you have any big picture questions?
So this is like, you have to go to some Q and then do the curvature there and then come back. Is that, like, you just have to like travel to the other side of the manifold to get all of the things that you need, or like is there some like large ball containing enough topology that you get all the things? Like how many Qs do you actually need to get all of this stuff?
In general, you have to take any curve. You have to take any curve. So like the idea is that like, okay, like you can imagine like on the sphere, for example, like let's say here's P, like you have a vector, and like when you do a parallel transport by like this sort of, this thing, it ends up coming up like that. But then if you do like larger and larger transports, you're going to be like rotating the vector more and more, and so like you need all the different curves in order to actually like generate the whole thing. And the idea is that like the infinitesimal like version of this whole story, because like this is the Lie algebra stuff, is that it's actually capturing the fact that the sphere has some intrinsic like curvature. Whereas if it didn't have any curvature, the vector wouldn't like change at all. It wouldn't like rotate at all, basically.
I think the reason why you also, this is a huge guess. I think the reason why you also end up with like these p gammas, where you have to struggle to the points, is I think maybe when you generalize it, here you start with like things with the bracket 0, but when you generalize it, then you have to approximate it at certain points. You're gonna have to travel at these points and concatenate, and you get this bigger gamma that you have to conjugate again.
Okay.
That's my, like, to me that makes sense. It's not if you start from this and then you try to generalize it, I feel like you would have to do some sort of approximation and then travel to these points and just conjugate everything at the end.
Yeah, this thing. So this thing just is like, this thing is like the equivalent of like P gamma acting on R Q of UV. Basically like, we did the like parallel transport for like sections, but then you also have induced parallel transports on like endomorphisms and like tensor bundles. And so like this is just the action of this P gamma on this RQ thing. It just like acts by like sort of the adjoint action on like either side. And that's, yeah, so like transporting the RQ itself ends up generating the Lie algebra itself. Yeah.
What is RQ UV an object of?
RQ is the curvature. Yeah. It's the curvature tensor that we talked about at the beginning.
Can you remember what object is it?
It's like a fraction of some tensor bundle, right?
Yeah. So RQ of UV ends up landing in the morphisms of EP. I guess Q here, because I have a Q on it. But in general, R eats two sections of the tangent bundle, eats two vector fields, and spits out a map that acts on EQ, a linear map on EQ if you have a vector bundle, for example. So it'll, like we said, basically like, this was what we wrote down at the beginning. RUV sigma equals like nabla U, nabla V sigma minus nabla V, nabla U sigma. That expression, if you remember that.
And when we actually with P gamma and then take the span, how do we take the span of that?
So all of these are just going to be vectors in end of EQ. This is a vector space. And you just like take the span, like end of EQ is some vector space, you just take the span over,
R span.
yeah, over R in this case. And that tells you that these will, that this theorem says that this is going to be all of whole B, although I haven't gone through the whole thing. Obviously there's going to be many of them that are the same. Like these are not going to be like completely independent, each of the terms.
Wait, I didn't ask, what happened in the complex case? Because all this.
Oh, in the complex case? Yeah, so, well, yeah. Everything holds, and it's actually like the most interesting like stuff happens in the complex case. Yeah, I'll trying to get there.
Okay,
Hopefully. Okay. Good. Any other questions?
I guess this is going to depend on this other question. First, in general, how hard is it to compute the holonomy group? Just out of curiosity.
Yeah. So, given the metric, I guess, like given a metric on. So, in general, what you will do is that you'll look at the curvature instead, and because so. The why this theorem is like really useful is that it actually tells you that this RQ thing is not just restricted to be an end of EQ. it actually has to be sitting inside of like a smaller space. So what you'll do in general is that you could compute the curvature of these things. So for example, like if you have like a Ricci flat sort of space, you can actually say, oh yeah, that like it's a Ricci flat, let's say, and it's a complex manifold that's Ricci flat. Then it's like holonomy has to be or something like that. There's like things like that basically that happen because of, I'll try to talk about this in a second, but it happens because we're able to say that this RQ is constrained by like living in a sort of smaller space, if that makes sense. So you're able to tell the holonomy group by properties of like curvature and things like that. So it's not too hard to compute actually.
Okay. Because my other question is going to be like, this comes back to that's a good question that we made a while ago. This thing here, this spanning set is huge, but we're in finite dimensions.
Yeah, this is massive.
Yeah.
Yeah.
But we're in finite dimensions, so actually there should be a linearly independent set, like a basis in here.
Oh yeah.
So like how hard is it to compute that basis, like that basic set?
Oh, that. I don't know about that. Yeah. That might be more difficult. Like of this Lie algebra specifically.
Yeah.
I don't know about that. I guess like that kind of, yeah, I don't know. Yeah, I have no idea. I guess then you'd have to like actually know what the group is. Yeah. Yeah, which again, when I sort of talk about the classification, we'll see that like once you know things about the curvature and stuff, you can say what these holonomy groups have to be. Okay, good. Oh yeah. Oh wow. Okay.
Like,
I'll try to speed through it. Maybe less proof sketches. A lot more sketchy.
That's good, say sketchy proofs.
Yeah, sketchy proofs. Oh yeah, there's just a quick thing that I wanted to mention, which was another just quick theorem, which just says that, so these P gammas, like I said, they have a way to act on tensor powers, like here, like we're acting on an endomorphism, which is like EQ and EQ star. But essentially, if we have some tensor, S is like a sort of tensor, in general, like we can take it as something valued in some amount of tensor products of these E bundles and the E star bundles. And it satisfies that nabla S is equal to 0, where again this is sort of like the induced connection, then basically like this thing is fixed by a parallel transport. Okay. And it's pretty simple just to see this because like basically if the derivative of S is 0, that just means that like if my S here, when I transport it here, so I take my S that lives here, I transport it to here, and and it's the same as the value of the section at Q, that means that it's unaffected by the parallel transport. Okay, so that's just sort of a corollary. I guess I kind of did use that there, like you do have to use that for that expansion there. Okay, good. So now we're specifically going to look at the Riemannian case. So in the Riemannian case, we have just like our usual, like you get your usual Riemann tensor, and you can actually write down these components of the Riemann tensor, and you have identities that this Riemann tensor satisfies. You can lower this index to get this R, A, B, C, D like this. And we have these identities. One is like R A B C D plus R A D B C plus R A C D B is equal to 0. Is that right? Yeah. And we also have skew, obviously like they're skew symmetric in both pairs here, but the interesting one that, you know, here, because we're in the Riemannian case, we're actually able to have all of these indices be indices of the tangent bundle. We can actually swap these two pairs, A, B, C, D, C, D, A, B, and it's the same tensor. Okay. So this R object actually lives in Sim2 of wedge 2 of T star. N. Okay. And it actually lives in Sim2 of the holonomy, that's the big part of it. We can identify those two spaces. Like this space is basically like wedge 2 T star n is the same as like skew symmetric endomorphisms. But this is actually, sorry, there's a big thing that I forgot to mention, but I'll get to it in a second. These are the same as like skew symmetric endomorphisms. Of Tm, and this is the Lie algebra of O of the orthogonal, like skew symmetry things. And I guess I'll show this now. What is Sim2? Sim2 symmetric tensors. So like this space symmetric tensor product of itself. So like each of these is anti-symmetric, but then it's symmetric to swap the pairs of each other. Okay. So the theorem says that for Riemannian holonomy, G P gamma V P gamma W is equal to GVW, okay? Which means that P gamma are isometries. Okay, and this is specifically for Riemannian holonomy only. We get that the P gammas are isometries. Proof sketch is you'll write down this thing and you sort of like use the fact that the connection is metric preserving, and then actually write down this thing as a function, take a sort of derivative with respect to t, and show that that's equal to 0. And once you show that it's equal to 0, that means that this thing is constant regardless of how much you move along gamma, and then that means that this thing is just the same as if you started at PW. Okay. So P gammas are actually for P gamma and P. Okay. So the P gammas are actually isometries, which means that whole P is actually, for the Riemannian case, a subset of O of n, if your manifold is n-dimensional. And if your manifold is oriented, then they're actually a subset of SO of O. Okay, so we're going to deal with a sort of like oriented case, in which case whole P is a subgroup of SO of n. Okay. And So that's why here we can say that this skew symmetric endomorphisms are the same as the Lie algebra of OM, of SOM. And that's the same as little hol p, because, let's see. Oh yeah, and so this has to be little hol p, because this thing generates hol p, and then it's also a subset of the Lie algebra of SOM. Yes?
For sim 2, you said if you swap two of the indices, you get that it's the same. Like, what is the definition of
Sim 2? Sim 2 is basically you take whatever is inside of here, you tensor product them, but like symmetrically. So like essentially like instead of just doing V tensor W, you have like V tensor W equals W tensor V by 2. Like you have symmetric tensors in here for whatever this vector space is. In this case, the vector space itself is wedge 2 of some. We can just do it at a point, and then this would be R at the point. But in this case, it would be like two forms at P, for example. This is just a vector space, which is there. But it can work like for any vector space here. Yeah. The reason it like sits in here is because each of these are skew symmetric. So like in A, if you swap AB, it'll be minus. If you swap CB, it'll be minus. But swapping both of the pairs of indices, it remains the same.
Well, that's because it's just skew symmetric, right? When you swap twice, you get two negatives, which becomes the same thing.
Well, no, because he was saying earlier that if you swap A and B, then you get the negative, right?
Yeah.
Or is it A, D?
A and B or C.
Or C and D.
Yeah.
Those would be the negatives, but.
Yeah. But if you do it twice, you get the same thing. So I'm saying.
Well, this is not twice. There's like quite a bit of swaps that you have to do to go from here to here, right?
It's two, right?
No,
No,
you like have to
no.
pass the C through A and B, and then you have to pass the D through the A and B.
I don't think there's like rules for swapping B and C, are there?
Yeah, exactly.
Yeah,
There's not like
exactly. It has to
specific,
be-
yeah.
Which
Which is
there's a
like,
rule like the second line you can use, but it's not particularly clean.
Mhm.
Like that.
Like this is the rule basically. Like, that like swaps that helps you move past the.
I was saying you can also use, if you want to swap B and C, for example, you can use the line above, but it's gonna be
Sure.
like not clean at all.
Yeah, that's right. That's right. You can, yeah. You can use it.
But you can't just swap in the middle there.
You can swap A and C.
Not immediately, right? But you can, like using combinations of like this identity and the fact of like swapping, right? Like by using this swap and then the individual swaps, you can probably do anything you want, right? But this one is like, it's like a non-trivial identity, right? Good? Yeah.
I had a question about that. So your holonomy is always in the orthogonal group for this Riemannian thing. So if you
For the
wanted,
Riemannian holonomy.
so if you wanted to realize like spin holonomy,
Yeah.
you just go to like the spin structure with your connection to there, and then you take the spinner bundle, and then look at the holonomy on that spinner bundle.
For this stuff. So, there are like specific ones that like, I'm sure understand what you mean by the spin stuff.
Because like I want to talk about a bundle whose holonomy is spin, for example, but you can't do it with this because your thing has to be a subgroup of ON. So
Yeah.
like by passing to the spinner bundle, you're taking like a spin representation, so it's not just an n-dimensional vector space anymore.
Yeah.
It's some big thing that spin n is acting on.
Yes, so here, I guess specifically, we're transporting around vectors on the tangent model. But you can talk about like you have a bundle, like you have like a spinner bundle, and like you can write down a connection on do all the stuff. But then that wouldn't be like Riemannian holonomy, because then you're not doing the tangent bundle specifically, right? It's like a more general bundle.
Yes, so I mean you still carry up like the Levi-Civita connection over to that
Yes.
spinner bundle.
Yeah.
So there is like something, it's not literally the tangent bundle, but it's like a
Yeah.
standardized version of it.
That's right, yeah, and there are like relations, essentially like, what happens is that like, so I'll try to, hopefully I'll get there with the like classification, like these like Riemannian holonomy groups are classified. And there are like specific ones for which you can actually pull up to these like spinor bundles and show that there exists a parallel spinor. If you have that specific holonomy group on your in here, you can actually lift that and say, oh, I have a parallel spinor in my spinor bundle, and that's why like they're sort of like useful in physics. Yeah.
Okay.
Good. Okay. Where was I? Yes. So this Riemann tensor is in sim2 of all P, and that's essentially one of the conditions. What did the eraser? One of the conditions that is telling us that holonomy, the holonomy group, is putting restrictions on our curvature tensor, because it can't just be any, at least for Riemannian holonomy, it can't just be any element of the endomorphisms. It has to be specifically living inside of this Lie algebra. And so the holonomy group puts restrictions on the curvature tensor R. Okay, or you can think about it as if you know information about your curvature tensor, you can also say things about the holonomy group. And so this is actually spelled out in this theorem that I was going to write down here. Sorry, my notes are all mixed up now. Is it this one? Yeah. Oh, I'm missing a page now. Oh, there are a bunch of pages over there.
Is this, did you type this all up, or did you get these?
No, these are like the notes that I was using. There's like a bunch of stuff I couldn't have time to like write down, so I had to like use these notes. Yeah, here we are. Okay, good. We did that. Yeah. Good. Yes. If we have MG Riemannian manifold, then our ABCD, I guess that was what we just said. Our ABCD lies in this vector space, symmetric of all P of G, and then there's this notation we write for Riemannian holonomy, we write Hall P of G because the metric determines the connection. inside of the space wedge 2 of TPM. Tensor wedge 2.
I probably should have asked this like ages ago.
Yeah.
But RBC, ABCD are just like coordinate or what?
Yeah, so this is in like index notation. So like our this. So if you remember initially, R ate two things and gave us an endomorphism.
Yep.
An endomorphism, if you write it down in coordinates, is something that has two indices because it's a matrix. Further, this thing eats two vectors.
Oh, so then you.
So it also has
CD or whatever,
yeah, like two covariant indices here,
Yeah.
A, B, C, D. So it's like R, A, B, C, D.
Okay.
But we also have a metric, and so like we can speak about what it means to like lower the index of R. Okay. Good.
So glad I took GR or else I would
Oh yeah.
Well, Geo did
Okay.
all this, but not rigorously.
Well, I mean, GR doesn't really do holonomy though, right?
Did you take GR with Eduardo?
Yeah,
That was last version, but one.
I mean, he talks about holonomy in passing.
Oh,
Does
I
he?
thought you meant like when you first came here back in 2000 and whatever.
No, it's 2024.
Okay. So now we can actually talk about the big theorem, which is the classification of Riemannian holonomy groups. So we've seen that basically, like this theorem tells us that there's a sort of big restriction on what the holonomy groups of a Riemannian manifold could be. So the idea was that maybe we can actually say specifically what Riemannian holonomy groups can exist in general. And that was done by Berger. And he specified them for Riemannian manifolds that are simply connected. And what he calls, I think he calls irreducible. Okay, so I'll say what this means in a second. So if we have Mg simply connected irreducible, then all P must be one of the following. The most general case is SOM for just any n. The second case is
Sorry, you said any M? Like it's just any of the. Any M? I didn't
Yeah,
hear what you said.
any M.
Oh, yeah.
yeah, exactly, any m. It can be U of m, which sits inside of SO2m. It can be SUM, again sitting inside of SO2m. It can be SPN. Sorry, 2n. And so for n, it can be SPN, SB1, which lives inside of SO4n as well. And we have two weird ones, G2, which lives inside of SO7, and spin 7.
G2 instanton?
Well, G2 instantons, yeah, I mean, it's this group,
That
G2,
group,
but
yeah.
yeah, it's,
I
yeah.
think the 14 dimension.
Yeah. spin 7, which is a subset of SO8. Yes. Okay, so these are the 7 possibilities for the possibilities for the holonomy group of a Riemannian manifold. Definitely don't have time to go through the proof, but I will say something about it. Essentially, you first want to talk about what can generally be subgroups of SOM, at least subgroups of SOM. So I'm going to look at like sort of closed subgroups of SOM. Those are actually classified by Cartan, which are the sort of homogeneous spaces. Okay, Cartan homogeneous spaces. These are like very symmetric spaces. They have a sort of like map that sort of like fixes only a point. It's like a reflection kind of like map. And they're subsets of SOM. These are sort of like the general things that like these groups can be. But then we actually need to satisfy the condition that we're living inside of this space and satisfying those Bianchi identities. And those put a linear restriction. The Bianchi identity gives us a sort of linear subspace that lives inside of here, and then adds just sort of it makes like the things like smaller, makes the possible spaces that basically eliminates a bunch of these spaces because it can't be any of these. And so you eliminate a large chunk of those ones, and these are like the ones that end up remaining. So simply connected was, like we said, that gives us the sort of connected Lie groups. What does irreducible mean here? Irreducible sort of means that basically this manifold MG, Riemannian manifold, doesn't locally split up into a sort of like product of two manifolds with metrics that sort of like split up into the two components. So we want a manifold that doesn't do this, because if this happens, the holonomy group of this manifold acts reducibly on the tangent spaces. So if we actually look for Riemannian manifolds that are irreducible, which means that they don't locally look like any of these, then we actually can get all of these groups that act irreducibly on Rm, or whatever dimension this thing is, basically. Yeah?
What kind of product is that between H1 and H2?
Like you can think of it as like a direct sum here,
Okay.
if you want. Because this is like just a product of manifolds, and then this is just like the product metric or the direct sum. Good. Okay. Good. Any other questions about this? Okay. So, I don't have much time, but I'll talk about this. So, like I said, the most general holonomy would be SOM, and then basically these are like a more restricted versions of what can be. Sort of like they have more interesting properties, or more interesting manifolds in general. So, manifolds with holonomy are Taylor manifolds. So these are complex manifolds with a Hermitian metric. Manifolds with SUM holonomy are called Calabi-Yau manifolds. Okay. And one can show, because like now we're reduced down to such a small group, that because this thing is so small, it actually ends up just being trivial. And so if it's trivial, that means that there's no curvature to generate the Lie algebra anyway, which means that the curvature has to vanish, the Ricci curvature has to vanish, which is actually what it means to be a Calabi-Yau manifold. You have a sort of vanishing Ricci curvature and a Hermitian metric. These ones are funny, the sort of SPN, SP1 and SPM. This is a weird thing that happens when you have the quaternions, is that because you have sort of two ways of acting the quaternions, with complex matrices you don't have this issue, because you can, if you have a scalar, if you have a matrix on the left and you act on a vector and you have a scalar, this is the same as if you had a scalar and then a vector, and then you acted from the right, because you could just move the scalar over here. So there's no like specific difference between like left and right actions in a sense. But with quaternionic stuff, you have one action where you can act a scalar on the left and a quaternionic matrix on the right, and one where you can act just the quaternionic matrix on the left. And those two things are different because I can't pass the like quaternion through the vector, basically. So this, I guess that's why I get like these two things here without going into like extra detail. Yeah.
I'm gonna need some more detail.
Okay.
What do you mean you cannot, like, I think A on the left and A on the right? This is not mention multiplication, this is like a conjugation action. Oh, I'm not sure what you mean by you can pass it in one case and not in the other. Like, I understand that in the quaternionic you don't have commutative, basically.
Yeah.
Something's gonna fail there.
Yeah.
But I'm not sure what the action is here.
So in general, it's just matrix multiplication, right?
But how does it make sense then?
What do you mean?
Because matrix has a column vector.
Yeah, you get a row vector or whatever, right? Or like, yeah. And then, well, so it's not like a...
I'm saying that you can't multiply those.
No, hold on. Oh yeah, no.
Yeah.
No, well, hold on. It's like left and right action rather than like actually like multiplying, I think, like matrices themselves.
But it should have a matrix representation now. But it should have a matrix representation now.
It should have a matrix representation. Yeah, let me think about this for a second. Sorry, it's not this. It's this. It's just this, like CA versus AC.
Yeah, that makes sense.
Sorry. Yeah. CA versus AC. Those actions are different from each other. Yeah. And that's why those end up like giving you sort of two different things. This group is not just it's not just the product. It's like it's the product modded out, like, so it's like SPN, SP1 with an actual like cross, and then modded out by -1 because those act the same as the identity in these two cases. So that's why you don't write like cross here, because it's just like modded out by this extra -1. Yeah, sorry about that. Yeah, and then the most interesting, of course, is like these two, which are called the sort of special holonomy cases. They only exist in one dimension, which is in this case 7, in this case 8, and it wasn't known until like I think like 1986 or something that there actually existed manifolds with these holonomies. Someone actually proved that there are actually manifolds that have these holonomies, and I think till this day, like, people are trying to find like actual cases where, like, concrete cases
Do you know
with these two cases. Yeah.
which ones they found them?
They're not like
Or they're not nice.
known manifolds.
Okay.
Yeah,
They
yeah.
just know there must exist manifolds.
They know they must exist. Yeah,
Okay.
yeah. That was the sort of like, yeah, the new thing, and then, yeah. But yeah, there's not like a canonical example of like a manifold of G2 holonomy, for example. Yeah. But yeah, over SUM, all of these, like you can write down canonical examples of like all of these. We know Kähler manifolds and Calabi-Yau manifolds very well. Oh yeah, I forgot to say, like this is a hyperkähler. And this is, I think, called quaternionic hyperkähler.
Getting real low there.
Oh, sorry.
No, it's good.
Yeah, so these ones hyperkähler, they have sort of like Kähler manifolds, like you have a sort of complex structure, J thing. And hyperkähler, you have like three different three different complex structures. Quaternionic hyperkähler, I don't even know, to be completely honest, what those are. Yes, but they sort of like come in pairs, and this is so yeah. The interesting cases is that like they come in pairs like this, like that, and the smaller ones like SUM is a subset of UM. This one is Ricci flat. SPM is like sitting inside of here, and this one is Ricci flat, and this one, I think these are related. I'm not sure exactly how it works. And I think G2 is Ricci flat. And then quaternionic hyperkähler ends up being Einstein, which means that the Ricci curvature is just a constant times G8, the metric itself. Okay. So I probably don't have time to talk about much else and do anything, but I think, yeah.
That's a very important question.
Yes.
How does spin 7 sit inside SO8?
Exactly.
How does spin 7 sit inside of SO8?
Yeah, what's that
Oh,
about?
you asked one.
So
Well, I guess I know. So I know that like spin 7 sits inside the even Clifford algebra, which is isomorphic to 8 by 8 real matrices. So
Yeah.
you have to know that like you're actually sitting inside those ones to determine one.
Yeah. Basically, like its actions on, so it's like you have to identify with octonions. So it's like G2 acts canonically on unit octonions, and spin 7 acts canonically on octonions. That's how you get that. And octonions is like R8, and so it, and it preserves the metric, and so it's living inside of SO8.
That's similar to the like spin 3 and spin 3 by showing that it acts on quaternions.
On quaternions, yeah. Yeah.
Oh,
Exactly. Yeah, which is why like there's no more after this, because like there's the sort of homogeneous space stuff that I mentioned uses a lot of this like division algebra stuff. That's sort of the reason. And then that here you end up actually getting a family, whereas here you only get one because the octonions are not associated, and you get like issues with like vector space stuff. So, but
Okay, so this is correct. We didn't think about real class and then octonionic doesn't work.
yeah, exactly. Real complex quaternionic octonionic, which is like just weird. Yeah.
There's an OP2 with no filter.
Yeah. Exactly. And Berger thought that there was spin 9 for some reason. And I think someone fixed that but I think he also did that thing because like there's like this Cayley plane or whatever, I forget what it's called, where it's like this weird two copies of a mod and alpha something. That's also like an interesting space, and he thought that would also work, but then someone ruled it out for a different reason. I forget exactly. Yeah.
Is it really the Einstein?
Well, in the other cases they're flat, so it's like, you know, lambda is 0. Yeah. But yeah, this specifically is, yeah, let me just double check that. But yes, only that one is Einstein.
So none of the special abilities.
Yeah, let me just double check here, just to be sure of that. Yeah, Ricci flat are SUM, SPM, and G2 and spin 7. Yeah, that's it. And then, yeah, SPM, SP1 is Einstein, but not Ricci flat.
Okay.
Yeah.
And for the Einstein cases, have people studied Ricci flows on those? Is that a meaningful thing to do? Does it?
Ricci flow, yeah, I'm sure you could do that probably.
Yeah.
I don't see why not.
How much is with their, is your flow, like you're reaching?
If you're flowing by the metric, there's not much to say,
Yeah,
right?
that's true.
Because like the equation is just like dt, like dt g times g.
Exactly.
Like that's very easy to solve, right?
Well, is it physically meaningful?
Is it physically meaningful? I don't know. I guess it just tells you that like
Yeah.
it just is gonna equally like shrink down. Yeah. Yeah.
I guess like I don't know if you plug it into the Einstein equations, then you might get some.
That's like that is the Einstein equation. Like when we say Einstein, like in math, they mean like this. Like,
Yeah. I mean like in the physics, the T is that.
oh, there's no T in here. It's just like no T. Just like R A B equals lambda G A B. Yeah. So no, just like flat, or like not flat, like no matter basically. That's what they mean by Einstein in math. Einstein in math just means like the Ricci curvature is some multiple of the metric, which is just a solution to the vacuum Einstein if you want.
Right, yes.
Yeah.
Exactly.
Mhm. Yeah. Other questions? Yeah. Good? Okay.